All right, so let's look at another double replacement reaction and go through the same process to figure out what the driving force is. And if we have a driving force, we're going to balance the formulas and the equation and so forth. First, we need to look at what kind of formulas we have. We need to recognize if we have the conditions for a double replacement reaction. So if I look at this formula here, I can see I have 1, 2, 3 different elements. And the rule is if you have 3 different elements, you want to first look for a polyatomic ion in that formula. And indeed, if I look carefully, I can see that I have a sulfate ion, SO4 2 negative, a sulfate ion. And that's this part of the formula here, SO4, and then there's a 2 negative charge which has been neutralized by the presence of the sodium. Over here, again, I have 3 elements. So I'm going to look for a polyatomic ion. Indeed, I found one, PO4, phosphate. So PO4 is a polyatomic ion. So I have 2 two-part compounds. And so we have what we need then for a double replacement reaction. Remember, double replacement has the general form AB plus CD. So Na is A, SO4 is B, H is C, PO4 is D. And in a double replacement reaction, A, the first part of this formula, joins up with D, the back part of this formula. So we'll end up with an AD plus the front part of this, joins up with the back of this, CB. That's the general form of a double replacement reaction. So let's do that. Let's put A with D now. So we're going to put Na and PO4 together. But I haven't balanced the formula. I'm going to wait to balance the formula until I find out if I have a driving force. If I don't have a driving force, I won't even need to balance the formulas or the equation. So now we're going to put together the H with the SO4. Same here. I'm not going to balance this formula until I find out if I have a driving force. Remember, there are 3 driving forces. The formation of a gas, we're not going to worry about in this class. So we can just ignore that. I want you to know that that's one of the 3 driving forces. We're just not going to do any problems with the formation of a gas as a driving force. Then we're going to look at whether we have the formation of water or a solid. So we do have water around because both of these compounds, it says, are aqueous. So this is taking place in a solution where water is the thing that's doing the dissolving. It's called the solvent. All right, so there's water around. This is an aqueous environment then. So let's look and see if this sodium phosphate is going to be aqueous. And to figure that out, we're going to look at these solubility rules. If you don't have your test references out, make sure you get them out. I'm going to ask the teacher to pause the video and wait for you because you need to practice looking through and using this solubility rules or these solubility rules. So let's look for SO4. And we said the name of that was sulfate. If you don't know that, well, go to your references called the common ions list, and you can see the name of this is sulfate, SO4, 2 negative is sulfate. All right, back to the solubility rules now. And we find sulfates right here in the bottom of this top section. Sulfates. So sulfate compounds are soluble. That's why it's in this top section. Any of these are mostly soluble. Sulfates are mostly soluble. Exceptions are those sulfates where calcium, strontium, barium, mercury, lead 2, or silver are part of the compound. Well, sodium isn't in that list. I'm sorry. Hydrogen is not in the list over here. So a hydrogen sulfate is going to be aqueous. Okay. Phosphates. We're going to find phosphates right here. Phosphates are in the top of the insoluble section. So these ions are mostly insoluble. In an aqueous environment, they would mostly form solids. We call them precipitates. So phosphates are mostly soluble, except when they're bonded with a group 1 element, or ammonium. So we need to know, is that group 1? Well, we said in the last video group 1 are any of those elements in column 1 of the periodic table. So you'll find your periodic table in your test references, and sodium is in that column 1. It is a group 1 element. So this compound, sodium phosphate, is a phosphate that meets the exception. Most phosphates are insoluble. They form solids or precipitates. But a sodium phosphate, because it's group 1, is not soluble. Is an exception. So it's not going to form a solid. The opposite of forming a solid when in an aqueous environment is to be soluble, and that makes this compound aqueous. So we have not formed water. We have not formed a solid. There is no formation of any products. All we have to do is write NR for no reaction. Okay. One more now. One more example before I turn you loose to practice some problems. Let's do H2SO4 aqueous, and let's bond that with let's see, well, magnesium hydroxide, I think, let me make sure. Nope, strontium hydroxide. Okay, again, we're looking at an A, B, C, D pattern. A, this is a polyatomic ion. We identified it up here as being a polyatomic ion. So that's B. Strontium is C. This hydroxide is in the parentheses, so you know right away that must be a polyatomic ion. If you're not sure, if there weren't any parentheses there, you look it up on the common ions list, and you'd find hydroxide is a polyatomic ion. Excuse me. Here's hydroxide, OH with a 1 negative charge. So that's our D part. Okay? All right, so the front part of this joins up with the back part of that, and we get HOH. Remember, it's very important that you understand subscripts like these do not travel. That is to say, you don't just automatically move them over to the other side unless they are part of a polyatomic ion. This is not part of the hydroxide ion. The hydroxide ion is OH. The 2 on the outside means I have 2 hydroxides. It doesn't mean the 2 is part of the polyatomic ion formula. This H means this 2 here means I have 2 of these H's. It's not part of a polyatomic ion. On the other hand, this 4 is part of the sulfate ion. If you look up sulfate, SO4 is the formula for a sulfate ion. So this subscript does travel, these 2 do not. So we're not going to put any of these subscripts here. But you should be able to recognize by now, HOH is water, and in a double replacement reaction, water is going to be a liquid. Please write it as a script lowercase l, so that you can tell the difference between, if you write it as a printed L, it's hard to tell that from a capital I or the number 1. So now let's join up strontium with the sulfate. And we know what physical state it's going to be in. Go to the common ion, the solubility rules. Find either strontium or sulfate. Sulfate is right here at the very bottom of the soluble section. Most of these ionic compounds that contain these things here in the soluble section are going to be soluble. And if they're soluble, it means they're going to be aqueous when you're in an aqueous environment. So it says sulfates are soluble except when bonded with calcium, strontium, barium, mercury, lead 2, or silver. Well, strontium is an exception. That means this is going to be a solid. Okay? Well, we have a case where we have both conditions for having a driving force. We formed a liquid and a solid. We only needed one of those. So this definitely is going to move forward. We do have a driving force. We're ready to balance the equation. Water, you know, that's balanced already. I hope you know it. Strontium, we need to figure out its charge. For that, we're going to go to the periodic table with oxidation numbers. Strontium has a 2+ charge. Sulfate, we noticed a moment ago. I'll go back and double check to make sure you know. Sulfate has a 2- charge. And we have been doing the math down here where we take the 2+ and the 2-, but I hope we've been doing this long enough you can tell that's going to give us a neutral charge without any coefficients in front of these ions. And so we just need one of each to get a balanced formula. Okay, so we're not going to do anything with that. Now we're ready. That is to say, we're not going to put any subscripts here to balance anything out. It's already balanced because it's neutrally charged. So we're ready now to do the atom inventory. Let's see. We got A on the front here, joining up with D on the back. We've got C on the front of this. Strontium is C. Sulfate B is on the back of this. That meets our pattern. All right. Atom inventory. We have hydrogens, sulfurs, oxygens, strontiums, and hydrogens. Create the little grid here. On this side of the arrow and in this column, we're going to list all the elements we have on this side, or count them. We have 2 hydrogens here, plus 2 here. So we have 4 hydrogens. This 2 outside the parentheses means everything inside is multiplied by 2. That's where you get 2 here and 2 here. We have 1 sulfur. We have 4 oxygens here and 2 there. So 4 plus 2 is 6. We have 6 oxygens over here, 1 strontium, and 2 hydrogens, and 2 hydrogens. Whoops, I've got hydrogen twice, don't I? Don't need that one. All right, so we're ready to go over to count this side then. We've got 2 hydrogens here in water. I've got 1 sulfur. I've got 1 and 4. 1 oxygen plus 4 equals 5 oxygens. So I have 1 strontium. Okay, we're going to save oxygen for last, hydrogen for next to last. Oh, but everything else is balanced. So we must start with hydrogen in this case because it's next to last, and it's only hydrogen and oxygen that are not balanced. So to get 4 hydrogens on the right side, I'll put a coefficient 2 here. That's going to change the number of hydrogens to 4. 2 times 2 is 4. It also changes the number of oxygens. I've got 2 oxygens here, plus 4. We now have 6 oxygens, and the equation is balanced. Okay? So you've had a chance to see 2 examples of double replacement reactions where you have driving forces, and 1 example where we don't have a driving force. So now we're going to practice. I'm going to give you a series of equations. The substitute has it. There's a link to it on the presentation, the Google Docs presentation. And then you're going to spend the remainder of this class period, Thursday, practicing, figuring out whether you have a driving force or not. If you have a driving force, balancing formulas, and then balancing the equation.